Hello, and in this chapter we're going to be looking at collisions, so when two objects collide or bash into each other, right? So firstly, I just want to play this little clip to just help you visualize what we're going to be looking at, right? So that's what we're going to be looking at. We're going to be looking at essentially two balls colliding and bashing into each other, right? So hopefully that helps with the visualization. I think once you can visualize and see what's going on, it'll make things easier to grasp. So hopefully that is helpful. Okay, so what we're going to look at then is we're going to be looking at the speeds before and after a collision, right? So the idea is that the overall speeds after a collision is smaller than the overall speeds before a collision. Okay, so what am I saying here is I'm saying that when two things collide, they're going to be basically losing energy. Okay, and that means overall they're going to be losing speed. Okay, so I'm going to say that this is due to loss in specifically kinetic energy, because that's the type of energy that's responsible for movement, right? Loss in kinetic energy due to the collision. Okay, and there's many reasons why we lose kinetic energy. For example, there might be a loud bang, so there's going to be some of the energy will be used to sound. There might be a lot of friction, or there might be loads of forces, so there's going to be extra energy devoted to that instead of just kinetic energy. So the idea is that less kinetic energy is lost, and so that results in the speeds going down. Okay, and so there we are. Okay, so we need to come up with some sort of mathematical way, some sort of formula to kind of encapsulate the idea of the speed after and before a collision, right? And it turns out that there is something called the coefficient of restitution. Okay, and what this is, it's a number. It's a number what we call E, and what we call this is the speed of separation over speed of approach. Okay, so what on earth does this mean? Well, the speed of separation, well, the clue's kind of in the name. Separation, it's like the speed after they collide. So it's the speed after they separate, right? So after the collision. Likewise, speed of approach, it's when the two objects approach each other. So that's going to be the speed before the collision. Okay, because they approach each other to make a collision, then they split off and separate. Okay, so that's the idea. So very informally, you could simplify this to help you grasp it. You could simplify it to the sort of the after speed divided by the before speed. Okay, actually, I'll write it the way around: speed after divided by speed before. Okay, very a sort of very rough and informal way of what this means. Okay, so that's the general gist then, but what exactly does this all mean? How exactly can we calculate all this then? Okay, well, to help that, let me consider two particles. We have ball 1 and ball 2. And so these two balls are going to collide. And ball 1 has speed u1. And ball 2 has speed u2. And this is before the collision. Then afterwards they collide. Then that means the ball 1 has speed v1. And ball 2 has speed v2. Okay, so these are my speeds afterwards. Okay, hopefully we're happy with that. We can calculate E in this way by saying we do v2 take away v1 over u1 take away u2. Okay, that's how we can calculate E in a more mathematical way. So what I'm saying here is I take away the speed of the second one from the first one, and so that's going to get me my speed of separation. And then we divide by the speed of approach, and the speed of approach is the speed of the first one before take away the speed of the second one. Okay, and that is and that will get me E, my coefficient of restitution there. Okay, so this is the more mathematical way you can calculate it. I actually prefer. I think this is a good. I think this is a good way to work out E here. The textbook doesn't go into it really. They don't really explain what these two speeds mean: the speed of separation and approach. They don't really explain how to calculate E, but that's what the textbooks are using. They're basically using this formula, okay? But they don't really explain anything that's going on. They just say, "Oh, here's E." There we are. They don't really explain anything, so I don't think that it's very helpful. But I think this formula is pretty nice, and actually, this formula kind of takes out any thinking you need to do, because especially when we're going to be looking at some harder questions with a lot of with some algebra later on in the video and later on in the chapter, when there's algebra involved. And it can be quite hard, but this formula tells you exactly what you need to plug in. Okay, there's no confusion or guesswork. Okay, because there's many ways. People have many ways of calculating E, but I think this is the most straightforward one that requires little thinking, and I think that's very useful when we get to harder questions with algebra. Because this formula tells you exactly what you need to do. Okay, so there we are. Okay, now just a little bit more, I guess to build the intuition. What exactly do we mean by these two speeds? Obviously I've done the mathematical expression here, but what exactly does this mean? Well, first, before we look into it, recall that speed is distance over time. And so what speed is in general, it tells me the distance moved per second, okay? Because remember, the units are in meters per second, okay? So that's all that speed is. It tells me how far I moved every second. So with that in mind then, I can explain the speed of separation. So the speed of separation, well, again, it's in the name separation. It's the speed afterwards, okay? After they collide, after they separate. So that tells me is how far two objects move away from each other per second, okay, after a collision. And similarly then, the speed of approach is how far two objects move towards each other, because then they would be approaching each other, right? So how far they move towards each other per second before a collision. Okay, so that is what these two speeds mean in words, okay, in a physical way, okay. So hopefully that helps to understand what these two mean. Again, the textbook does not explain this at all. They just say here's the speed of separation, does explain what it is. But hopefully this has helped a bit there. But that's what all these terms mean in, okay. And so there we are. And so we're going to be using this, well, I'll be using this formula to calculate this E, this coefficient restitution. Now, the other reason why this formula is great is, again, if you use it right, it should always work, okay? Again, there's no guesswork. If you just use the formula right, it should work out fine. And this means E would always be positive. And it turns out that actually E is between 0 and 1, okay? Where should I write it? I'll do it here. E is between 0 and 1, okay? And that inequality you do need to know, okay? You do need to know that questions will require you to manipulate this inequality here, so you need to know that. So what exactly does E mean? So we discussed what all the speeds mean, but what does E mean? Okay, what does this overall result mean? E refers to how elastic a collision is. So what on earth does that mean? Okay, a lot of words here. So what is what on earth does elastic mean? What on earth does that mean? Well, that just means it tells me how sort of bouncy a collision is, so how well two balls bounce off each other, okay? So what that means is it refers to how much energy is lost, okay? So that means so how much energy or speed is lost in a collision, right? So what that means is if something is elastic, well, no, sorry, if a collision is elastic, that's saying there's not a lot of speed lost, not a lot of energy lost, okay? But if something is less elastic, then it's not much, so then a lot of speed has been lost, okay? A lot of energy is lost, okay? And so there we are. So that means if E is closer to 1, it's more elastic. So that means there's not a lot of speed lost, okay? But if E is closer to 0, that tells me there is a lot of speed lost, okay, due to the collision. A lot of energy lost, okay? And so there we are, okay? Lastly then, I want to look at the extreme cases when E is equal to 1 or E is equal to 0. So obviously, as we discussed, E is between 0 and 1. So what happens when it's exactly 0 or 1 then, okay? So firstly, when E equals 1, that collision is what we call a perfectly elastic collision, okay? So as you can see here, before the collision, the particles, the balls are approaching each other with an overall speed v. Then after the collision, we're saying that they're then going to separate with the same overall speed v. So the idea is the overall speed remains the same. There's no loss in overall speed, okay? So I'm going to say that when E equals 1, this is a perfectly elastic collision. And what that means is, as we discussed, there's no loss in overall speed. And again, so what I'm saying here is, in terms of overall speed, the speed that they approach each other at is going to be the same as the speed when they separate, okay? And so there we are. What about lastly when E equals 0? Well, this is quite an interesting scenario. So when E equals 0, this is what we call a totally inelastic collision. So as you can see here, again, they're approaching each other with the overall speed v, but afterwards, then they're actually stuck together, okay? So what I'm going to say is, when E equals 0, after the collision, the particles are stuck together, okay? And actually, there's a very fancy word for this. When we say two particles like this stick together like this, we call it coalesce. Okay, coalesce. Hopefully, I've spelt that right. Okay, and you might see that word somewhere. You might see that word thrown about. That's what it means. When two objects coalesce, they stick together as one. Okay. Now, it says the speed goes to 0. It's not saying that they go to rest, right, and stop moving. That's referring to their separation speed, so the overall speed afterwards. So that's saying if they don't separate, well, they don't because they stick together. They don't separate, so there's no overall speed between them, okay? So that's saying that actually their speeds are the same because they combine together, so they must move together at the same speed. And so I'm going to add to this then. They're stuck together and move with the same speed. Now, you do need to remember these two cases here. Questions may refer to collisions being perfectly elastic. If a question mentions something being perfectly elastic, you need to then remember that means E is 1. Okay. Likewise, if you see something being coalesced, right, two particles being coalesced, that means they stick together, and that E is 0. Okay. And so you do need to pay attention to these two cases here, okay? But very rarely this comes up, but you still need to be aware of it. Now we're going to look at some examples of calculating this E, then this coefficient restitution. Again, remember that we said that E was V2 take away V1 over U1 take away U2, okay? And that's when we have two balls like this, speed U1, U2, and then V1 and V2, okay? So we're going to apply this to these three examples here. So firstly, again, we've got three examples. We've got three different collisions. So for part A, so this is before the collision. So ball A has speed 8 and B is at rest, so it has 0 speed. Then after the collision, we have ball A at rest, so ball A has speed 0, and then ball B has speed 2 afterwards, okay? So hopefully, if you compare the formula we've got here then for part A, hopefully you can deduce that E, well, V2 is going to be this 2 here, that's the speed of B afterwards. Take away V1, hopefully you can spot that, well, V1 has to be 0, because it's at rest, okay, so it's 0. And then we're going to take away U1. Hopefully you can spot U1 is going to be the speed of the first ball A, which is speed 8. Take away the speed of ball B, which is 0. Okay, so there we are. And so then if we simplify this, we get 2 over 8, which is a quarter. Okay, and there we are. Part B, okay, E. Okay, so now for part B here. So if we look firstly afterwards, so this is going to be V2, the speed of the second ball. That speed is 5. And then the speed of the first one afterwards. So V1 is going to be 4 here. And then we're going to divide by these speeds before. So the speed of A before, this is U1. That's going to be 6, take away U2, which is going to be 3. Okay. And so there we are. We simplify it to get 1 over 3. Okay. Then for part C. Now this is where it gets a bit more interesting. Okay. So there's a slight complication where now the speeds are going in different directions, right? You can see it here. So before you can see that ball A is going 11 to the right, but ball B is going 7 in the opposite way to the left. Now directions matter because these are velocities, okay? Direction matters. Like when you looked at momentum in chapter 1, we need to consider a positive direction before we apply this. Okay, now we're always going to take the right to be positive. Okay, that's my positive direction. Okay, and we're going to be using momentum in a bit as well, so this will just keep the theme. Okay, so we're going to assume a positive direction, and so then if we calculate E, firstly, if I look at my speeds after, so V2 is going to be 3 here, and then take away the speed of speed V1, which should be 6. However, 6 is going in the sort of negative direction. This speed here, 6, that's going to the left. That's in the opposite direction. It's in the negative direction, right? Because remember, we're taking forwards to be the positive direction. So minus of -6. Okay. And there we are. Okay. So we need to pay attention to things in the negative direction. Okay. And then we're going to do U1 take away U2, where U1 is going to be 11. That's going to be positive. It's going to the right, take away U2. Now that's 7, but that's going to be in the negative direction. So we have to do a -7. So we get double negative, right? So if we simplify this, we get 3 add 6, which is 9. And then 11 adds 7, which is 18. And that simplifies to a half. Okay, and there we are. Okay, and that's how you calculate E. Okay, we are going to take forwards to be the positive direction, and we need to negate things in the negative direction to make it positive. Okay, but that's generally how we're going to work out E. Okay, actually, before we move on to the next example, I just want to demonstrate again what these the speed of separation and speed of approach, just to really reinforce what the concepts mean. So let's take part C. So my speed of separation, firstly, well, we calculated it, it's the numerator, right? It's 9. Okay, and the speed of approach is the denominator, which is 18, right? So those are sort of my speeds before and after and before, right? So firstly, if the speed of separation is 9, what does that mean in this context? So for part C, have a look at these two speeds. Remember, I said speed of separation is how far the objects move away from each other every second, okay? And so you can kind of see that here. So particle A has 6 speed to the left. You can think of it in terms of steps if you want. It doesn't have to be meters, it could be steps, just to help demonstrate it, right? So A, what this is saying, the speed of 6 means it's moving, say, 6 steps to the left every second. But also B is moving 3 steps away from A as well every second. So overall, they're going to be 9 steps apart, or 9 meters apart, if you will. So that's where the speed of separation comes from. So that tells me A and B move 9 meters apart every second. Okay, hopefully you can see that there. Okay, and likewise for the speed of approach here, well, A has speed 11 and that's going towards B, and B has speed 7 and that's going towards A. So that means overall they're going to be every second they're going to be heading towards each other 18 meters, okay? Because A is going 11 meters to B and B is going 7 meters to A. So overall they're going 18 meters towards each other. Okay, so A and B move 18 meters towards each other every second, okay? And that's essentially what these two speeds mean. Okay, so hopefully that helps to reinforce what exactly is going on here, and so what these two speeds mean. Okay, so there we are. So firstly we have for part B, okay, again that's going to be E is V2 take away V1 over U1 take away U2. Again we're going to assume a positive direction. Okay, so forwards is positive. So okay, E for part B, so this is part B. So that's going to be V2, which is 3, take away V1, which is 2, over U1, which is 4, take away u2, which is 2. Okay, and they're all in the positive direction. All the speeds here are going forwards. Okay, so they're all positive. So there we are. So we simplify this, we get 1 over 2. Okay, then for part C, E here, well, V1 is going to, V2, sorry, is going to be 2. Take away V1, which is 3, but that is going in the backwards, negative direction. So it's going to be minus 3. Okay. Then U1, that's going to be 9. Take away U2, which is going to be minus 6. Okay. And so that's going to get me 2 add 3, which is 5, and then 9 plus 6, which is 15, and that'll go to a third. Okay. And there we are. Okay. Now what we're going to be looking at is combining this restitution, this E, with the conservation of momentum, which you would have seen from chapter 1. So remember that momentum is mass times velocity. So when we are dealing with two objects or two balls, they're going to collide together. So let's say this is ball A, this is ball B. Now via the conservation of momentum, this basically tells me momentum is conserved, right? So momentum does not change before and after a collision. So that means the total momentum before is equal to the total momentum after. Now, obviously here we've got two balls, A and B, so we can further split this up into the momentum of A before plus the momentum of B before the collision, right? That's going to equal to the after momentum. So momentum of A after and the momentum of B after. Okay, and that's what we'll be applying, right? And again, hopefully you would have dealt with this in chapter 1, but we'll be applying this as well. Okay, so we've got this question here, and again we're given the before and after of a collision, right? And they want me to work out the final speeds v1 and v2, okay, for the two particles here. Okay, so we're going to be needing to use momentum and restitution, okay, which we just looked at before. So okay, we've got this example first. So we have a ball A with speed 4 and ball B with speed 2. That's before the collision, and after the collision, ball A has speed v1 and ball B has speed v2, right? And E is also 0.25. Okay, so there we are. So we need to work out v1 and v2. So first we're going to use momentum. Okay, and remember momentum is mass times velocity. And so we need to calculate all the individual momentums. So firstly, the before momentum, so the momentum of A before, that's going to be the mass, which is 2, times the speed 4. Then we're going to add on the momentum of B, and so that's going to be mass 3 times the velocity 2. Okay, that gets me my momentum. Then that's going to equal the after momentum. So this momentum of A afterwards is going to be 2 lots of V1. And the momentum of B is going to be 3 lots of V2. Okay, so this is my momentum before. And that's my momentum after. Okay, before and after the collision. And the idea is, due to the conservation of momentum, these two have to be equal. So the total momentum before has to equal the total momentum after. So hopefully happy with this calculation and this equation here, okay? This is the conservation of momentum, okay? So there we are. So let's simplify this equation now. Well, 2 times 4 is 8. 3 times 2 is 6. That's going to equal 2v1 add 3v2. So we can simplify this to 2v1 add 3v2 to be 14. Okay, so we get this equation here. Then we're going to need to apply restitution. So this is E, right? So E. So E, now remember E was what we said, V2 take away V1 over U1 take away U2. So my after speeds and before speeds. So V2, well, that's V2 here, take away V1, okay. And then divide by U1 take away U2. So 4 for U1 and 2 for U2. 4 take away 2 then. So there we are. And actually, we know what E is. We know that E is 0.25. So that means 0.25 is going to equal this V1 take away V2 take away V1 over 2. Right? 4 minus 2 is 2. Then we can cross multiply by 2 to get 0.5 is V2 take away V1. Okay? And we get this second equation here. Okay? Right. And so actually, hopefully you can spot now we've got simultaneous equations. If I rewrite these equations here, so I have 2v1 and 3v2 is equal to 14, and minus v1 and v2 equals 0.5. I get these two equations, right? So I just now need to solve them as simultaneous equations, right? Which you should know from GCSE. So the best way to solve these, well, let's match the V1s, right? So let's double the second equation and multiply it by 2. So that's going to get me minus 2v1 add 2v2 is 1. And then I can add by the first equation. So I can add 2v1 add 3v2 is 14. If I add these two equations together, well, the v1s now cancel. Okay, so I have minus 2v1 add 2v1 goes to 0. 2v2 add 3v2 is 5v2. That's going to equal 15. So therefore v2 is going to be, well, 15 divided by 5 is 3. Okay, and there we are. Okay, so that is the speed of the second particle, the second ball, v2. Okay, now we need to find v1. That's quite easy because now I could just substitute it into one of the equations. Let's substitute it into the second one here. So minus v1 add v2, which is 3, equals 0.5. So that means v1 is going to equal 2.5. Okay, and there we are. So I've got my two final speeds there. Okay, and so that's generally the idea. So the main idea is we're going to want to, with all these questions, is we're going to use momentum and the restitution to get simultaneous equations. Then we solve these simultaneous equations. Okay, so there we are. Now let's have a look at the next question. Okay, so now again, we got before and after for a collision. So if we apply momentum firstly. Okay, well, firstly, we work out all the individual momentums. So before, the momentum of A is going to be mass, which is 3 times the speed 8. Add the momentum of B. Well, the mass is 1, and well, the velocity is 6, but it's going in the negative direction. Remember, we're always going to treat, we're going to take forwards to be positive. Okay, so if it's going backwards instead of positive, it's going in the negative direction. So this is going to be minus 6 for the velocity here. Okay, and then that's going to equal the mass, the momentum of A afterwards. So it's going to be 3 lots of v1. That's going to be positive because v1's going forwards. and then 1 lots of v2, which is also positive because it's also going forwards. Okay, hopefully happy with the directions. So if we simplify this, that will go to 3 times 8 is 24 minus 6, that goes to 18 equals 3v1 add v2, and that's my first equation. Then I'm going to apply restitution. Okay, so that's going to be E. Well, that's going to equal V2 take away V1. So V2 take away V1. Then U1 take away U2. Now, U1 is 8. That's great. Take away U2. But again, it's negative, right? It's the same situation. It's negative. It's going in the negative direction. So we need to make it minus 6. Okay. And so there we are. Now, actually, we know that E is a 7th. So that means a 7th equals this. Okay, so it's going to be V2 take away V1 over 8 plus 6, which is 14. So therefore, 14 times a 7th is, I'll do it here. This simplifies to 2 equals V2 take away V1. And so I get this equation as well. So now I get these simultaneous equations. I get that 3v1 at v2 is 18. And v minus v1 at v2 is 2. So again, we get these simultaneous equations. So now we just solve them. And actually, spot, we can just take these equations away because I have v2, then take away v2, that goes to 0. So the v2's cancel. Okay, so we just take these two equations away. So 3v1 take away minus v1, that's a double negative. That will go to 4 lots of v1. Then the v2's cancel. That's going to equal 18 minus 2, which is 16. So therefore, if you divide by 4, I get v1 to be 4. Okay, and that is my speed there. Okay, that's v1. Now I'm going to need to find v2. I could substitute it into the second one. So that means minus 4 for v1, add v2 equals 2. So therefore v2 is going to be 6. Okay, and that is my speed for the second ball afterwards. And there we are. Those are my two speeds then. Okay. Okay, so hopefully you get the process there. So we use momentum, we use restitution, and we solve simultaneous equations. So that's generally the premise. Okay, now we've got a worded question. We're not given a diagram for us. We're going to have to make our own diagram. So the question says, a small smooth sphere A of mass 1 is travelling along a straight line on a smooth horizontal plane with speed 4 when it collides on a second smooth sphere B of same radius with mass 2 and travelling in the same direction as A with speed 2.5. After the collision, A continues in the same direction with speed 2. Okay, so we need to draw a diagram to work stuff out. Now, again, we've got these two spheres, A and B. So I'm going to draw them like this. Okay, so we have A and B. And for A, the mass is 1. So it's going to be 1 kg. And then for B, the mass is 2. So it's going to be 2 kg for B. Hopefully happy with that. Now we need to add our speeds. So before the collision, we're told A has speed 4 and it's going to collide into B, so it's going to be speed 4 this way. And for B, it says we're travelling in the same direction. Okay, so ball B is travelling in the same direction as A before with speed 2.5. So it's going to be in the same direction. So it's also going to go forwards with speed 2.5. Okay, because again, the directions are the same. Okay, because we're told it's travelling in the same direction. Hopefully happy with that. So those are my speeds before. Then it says after the collision, A continues in the same direction. So A also goes forward and the speed is now 2. Okay, it wants me to find the speed of B. Now the speed of B has to also go forwards. Call that V2, right? Okay, obviously if it went the other way, then B would have to kind of like go past A and kind of like somehow use like some sort of weird like glitch where B just phases through A. Obviously that cannot happen. That doesn't make sense. So B can only be pushed forward. Okay, B can only move forward because it can't just get past A, right? It can't just phase through A like some sort of weird physics thing. It just has to move forward. Okay, and so there we are. Anyway, so those are my speeds. Hopefully happy with that. That's how we're going to want to set up these questions. So let's apply momentum. So again, we're going to take forwards as positive, but all the speeds are in the forwards direction, so that's quite nice. So everything's positive here. And so for A, the mass is 1 and the initial speed is 4. And then for B, the mass is 2 and the initial speed is 2.5. That's going to equal the momentum of A afterwards, which is 1 times 2 and then 2 times V2 for B. Okay. And so if we simplify this, we're going to get 4 add 5 equals 2 add 2 V2. And then we could just quite easily solve this for V2 here. So 2V2 is going to be 7. So therefore V2 is 3.5. Okay, and that is my speed of particle B. Okay. Then it says for part B, it wants to then work out the coefficient of restitution. So in that, okay, so that means E. Well, we're going to do V2 take away V1. So that's going to be, so V2 take away V1 over U1 take away U2. Now again, V2 we just worked out to be 3.5. Then we're going to take away V1, which is going to be 2 here. And then U1, that's going to be 4. Okay. Take away 2.5. Okay. And so there we are. We calculate this. We get 1. Okay, E is exactly 1 there. Okay, now we're going to be looking at some harder questions involving algebra, but also we're going to be involving impulse as well. So if I remind you then, as you can see here, from chapter 1, we looked at impulse, and we saw that when two objects collide, they impose an impulse onto each other. Okay, as you can see here. And the idea is, okay, if I have two balls here, the idea is, well, the first ball, okay, if I call it 1 and 2, the first ball pushes into the second one like this, so that imposes an impulse like this onto the second ball. Likewise, then the second ball goes into the first one like this, so that it creates an opposite impulse force acting the other way for the first one. Okay, so the idea is that when any two balls collide, two objects collide, they push into one another, and so it creates impulses in this way. Okay, and so you can see impulse is what we call equal and opposite. So you can see that the impulses act in the opposite directions, forwards and backwards, for each of the two balls, but they're going to be the same physical size. Okay, and so we saw also from chapter 1, if I remind you, that impulse is change in momentum. Okay, and so we'll be using that here, and more specifically we could say that I is mv take away mu. Okay, so this is the formula we'll be using, right? So impulse is mass times the final speed, v take away the mass times the initial speed u, okay, which is my change in momentum. Okay, and so there we are. So we'll be using some impulse here. Okay, and just before we move on to the examples, I want to take some time to look at 3 specific type of problems, okay, which exam papers love to ask about. So we'll be looking at these extensively throughout the chapter, but I want to devote a specific section to this now, because I think once you see this and it makes sense, the questions should be more easier to tackle. Okay, so I've got this problem here first. So as you can see here, I've got this particle, this ball, and what we're saying is initially it's going forward with speed 4, and then afterwards we're still taking it to go forwards with this expression, this expression v of 2k minus 1. Okay, now the question I'm asking here is, for what values of k is the direction of motion the same, and when is it reversed? So what do I mean by direction of motion? So if the direction of motion is kept the same, well, before the collision it's going forwards. So if the direction of motion is the same, it will continue to still go forwards. Okay, so that's what I'm asking for basically. Is the direction going to be the same? So if it's going forwards, is it still going to go forwards? Okay. Now, what could happen is, we don't know what the actual number for the speed is. It's just an algebraic expression, 2k minus 1. I don't know what k could be anything. I don't know what actual number that could be, right? So what could happen is, we could actually get a negative number. So we could get, let's say, minus 6 for my velocity here. Now, if the velocity is minus 6, that tells me that if we were to flip the direction backward instead, it would then flip to positive. Okay, and so that's the idea, right? So when we have velocities here, if we flip the sign, it flips the direction. Okay, and so we need to make sure that if the motion stays the same, so if it continues to go forward, we do not flip the direction. Okay, we do not flip where the velocity is going. It's still going to go forwards, and so we need to make sure it's not going to be negative. Okay, because like I said here, if it's going to be like minus 2 forwards, indeed it will have to go back by positive 2. So that will tell me it will be going backwards instead. So to keep the direction going the same way forwards, this expression has to be a positive. Okay, because remember, again, it's velocity, so if it's negative we have to flip the direction. Okay, anyway, hopefully happy with that. So when it continues to go forward, that means we need to make this positive. Okay, so v has to be positive, greater than 0. Therefore, if we sub our expression in, it's 2k minus 1 has to be greater than 0. Then we can solve and we get a half. Okay, so that tells me when I set k to be a half, that will then make sure that I get a positive answer. And so if it's a positive answer, that means the direction remains the same. We do not flip the direction. Okay, hopefully happy with that. Then it says, when is the direction reversed? Well, that's then going to be the opposite case, right? That is now saying, what about if instead we want it to go backwards? Okay, now that we need to flip the direction. So if we said it was going forwards, we need to make sure this is going to be a negative answer, because that would force us to then go the other way. Okay, to flip the direction. Okay, and so we need to now do the opposite and now say it's less than 0. So if instead it goes backwards, that means v has to be less than 0, has to be negative. So then if I sub my expression in, 2k minus 1 is less than 0, so k is going to be less than a half. Okay, so when k is set to be less than a half, that would then ensure that my expression for the velocity, so my expression 2k minus 1, would indeed be negative then. And so if it's negative, we need to flip it to go backwards instead. Okay, so hopefully happy with that there. So the core essence is that the sign of my speed or my velocity, the sign of it tells me if I'm going one direction or another. Okay, and so there we are. Lastly, I want to clarify here, it's possible, for example, okay, if we took backwards as the negative direction, it is possible to still have a velocity that is positive, okay? So let's say we have something going backwards with positive free speed, but that's telling me because it's positive, it's indeed moving backwards, okay? Despite the direction being negative, the velocity is positive, which tells me it is indeed moving backwards. So something can move in the negative direction, but the velocity be positive, okay? Please don't conflate this with the negative or positive direction, okay? We account for what direction it's going in, positive or negative. We account for that in the equations, okay? So when we do restitution and momentum, we account for the positive or negative direction, but my answer tells me what the true direction is, okay? So if I'm going in the wrong direction to what's actually where it should be going, then my answer will tell me that, okay? I just really want to clarify and hone in on that, okay? But there we are. Next problem they love asking about is determining whether a collision will actually occur. So again, we've got these two balls, these two particles here. You can see for the first one, the speed is 3k going forwards, and for the second one, it's 5 going forwards, okay? Now, the key thing here is they're both going in the same direction, okay? So there won't always be a collision depending on the speeds. Now, again, like with the first problem, it's algebraic, right? It's not an actual number exactly, right? It's in terms of k. So actually, it's not always going to collide, the two balls here. If you think, I guess, in a physics sense, or in just common sense wise, if we've got two things moving in the same direction like this, when will they collide? Well, actually, hopefully you can visualize that these two will collide when the first one is faster than the second one, okay? So I'm going to say that the particles will collide if the first one is faster than the second one, okay? And so that will be because if the first one's moving faster than the second one, the first one would then be able to catch up to the second one. And so then they'll be able to collide into each other, okay? And so I'm going to say that therefore the first one can catch up and then hit the second one. Okay, so how exactly can we do this mathematically then? So we've got this sense that if they were to collide, the first one has to be faster than the second one. Well, that means that the speed of the first one has to be bigger than the speed of the second one. So therefore we can say the speed of the first one is greater than the speed of the second one. Because then the first one will be faster and then catch up to the second one, okay? And actually we can then sub in the speeds. So the first one has speed 3k, and so that has to be greater than the speed of the second one, which is just 5. And now we've got an inequality to solve. So therefore k divided by 3 is 5 over 3. And there we are. So that tells me that when k is bigger than 5 over 3, that would ensure that the first ball will be faster than the second one, okay? And so then they will collide, okay? And so hopefully you can visualize that, but that's the idea, right? So there we are. The final question they love asking about is inequalities where we have to use E. Okay, so here we're told if the speed of a particle is v, which is 2k lots of 3e plus 2, so that's my expression for the speed, we need to show that the speed is actually then between 4k and 10k, okay? Now, what we're going to need to use here is the inequality for E. So remember that E is between 0 and 1. Okay? And you need to remember that. You must remember that. It's going to be critical to be able to answer questions like this. Okay? Now, what we can do is, if we know that E is between 0 and 1, we can kind of do some stuff to then eventually get to the expression 2k of 3e plus 2. Okay, so what we can kind of do is go step by step to then get to this final expression here. So firstly, if I know E is between 0 and 1, then therefore if I multiply by 3 to the whole inequality, is going to be between 0 lots of 3e to 3. Okay, hopefully happy with that. Then the next step, I'm going to add 2 to the whole inequality. So I'm going to get 2 between 3e plus 2 to 5, okay? Then the last step, well, we're going to have to then multiply by 2k, right? So that's going to be 2 times 2k is 4k, and then 2k lots of 3e plus 2, and then 5 times 2k is going to be 10k, okay? And actually, if we then look at this, well, 2k of 3e plus 2, that's equal to v. So therefore 4k is between 10k there. Okay? And so we get the inequality they want. Okay? And again, you can kind of see that in many ways. You can kind of manipulate the inequality in many ways. But I think that might be the safest approach. So if you start from E, then you kind of like unravel, and then eventually get to the whole expression, and then there we are. Okay, but hopefully you can see that right. So that's the idea. We can manipulate the main inequality for E to get to whatever inequality they want. Okay, but you need to remember that. Okay, and then I've got this last question here, and again you can see I got this particle. It's going forward initially with speed 4, then afterwards it looks like it's going forward with this expression v, which is 3e minus 1. Okay, now the question said, given the particle is still moving forward after the collision, find the full possible range of values of E. Okay, so the first key information there is that the particle is indeed still moving forward. Okay, now if you remember when we looked at the first problem a few minutes ago, well, actually, if indeed it's moving forward, we do not want to change its direction. Now again, because this is not an actual number, right? We don't know what this number actually is, this expression. It could be negative or positive, okay, depending on what values of E we plug in. Okay, so we want to preserve the direction. It must not be changed. We must not reverse it, we must not flip it. So that means it has to be kept positive. My value must be positive here, so that we do not flip the direction, because it has to be going forward. Hopefully happy with that. So that means because it must be moving forward, we do not reverse the direction, and therefore it has to be kept positive. So if it's positive, that means 3e minus 1 is positive. Then we can solve for E to get my range of values. So that means E is going to be greater than a third. Okay. And so then you might be thinking, well, there we are. Plug in any value of E greater than the third. That would get me a positive answer for V. And so if it's positive, that means we keep the direction forward. Okay. Now, notice I've written in bold the full possible range of values. Remember, E is also always between 0 and 1. So examiners will expect you to tighten this inequality to make it better. We can do better than just saying a third. So my final answer, if I incorporate it being between 0 and 1, well, if E has to be greater than the third, so it's going to be between a third and then 1, like this. Okay, and that is my final answer for the full possible range of values. Okay, E cannot be above 1 and it cannot be less than a third. Okay, so there we are. Hopefully happy with that. Again, you have to remember this inequality for E. Okay, but there we are. Okay, so this is my first question here then. So we've got two spheres A and B, masses 2 and 6. A and B move towards each other in opposite directions with speeds 4 and 6. If the coefficient of restitution is a fifth, find the velocities after the collision and the impulse. Okay, so again, we've got a worded question, so let's draw the information out. So ultimately, we have, again, these two balls, particles A and B. There we are. The mass of A is 2 and the mass of B is 6. Okay. Now, before the collision, we are told they move towards each other in opposite directions. So that tells me A has to move to B and B has to move to A like that. Okay. And you can see that one's going forward and one's going backwards. And so there we are. And the speed is 4 for A and 6 for B. And there we are. So that's everything we are given. Hopefully happy with this. I'm also told E is a fifth. So there we are. Now, they're asking us to find the velocities after the collision. Now, they don't, in this question, they're not telling us exactly where things are moving afterwards. So we're just going to have to take a direction and moving in, right? And if we're wrong, my answer will tell me to go the other direction. Okay, so let's just assume where they're going to go for now. Now, the textbook, what I've noticed with the textbook, they always assume they both go forwards, okay? So let's take both going forwards. And generally, this is probably not bad advice because it makes the calculations a bit simpler because they're both in the positive direction. So here we are. So I'm going to call this V2 and V1 then, right? So if you recommend just assume that they both go forwards, right? If you're not told where they're going afterwards, okay? But there we are. Now we're going to apply momentum. So firstly for A, the mass is 2, lots of the initial speed 4. And then for B, it's 6, and then it'd be minus 6 because the velocity is negative because it's going in the negative direction. So it's minus 6 to account for the negative direction. That's going to be 2 lots of V1 and then 6 lots of V2. Hopefully happy with this. If I simplify, I get 8 minus 36 is 2V1 add 6V2. And so this simplifies to 2V1 add 6V2 to be minus 28. And that's my first equation there, okay? And then we're going to use restitution. And remember, again, my standard formula is E is V2 take away V1 over U1 take away U2. Okay. Well, obviously I've got V2 and V1 here, so it's just V2 take away V1. And then U1 take away U2, well, this is U1, which is 4, and U2 is 6. But the 6 here is going in the negative direction. So we're going to have to do 4 take away minus 6. We have to make it negative, because again, it's in the negative direction. So that would be V2 take away V1 over 4 plus 6. Okay. And actually then, if we recall that we were told that E is 1/5, we can then say a fifth equals this, okay? Then if we cross multiply, we get 10 equals 5 lots of V2 take away V1. Therefore, we get minus 5V1 add 5V2 equals 10. Actually, we can also simplify even further. We could divide by 5. So it just goes to minus V1 add V2 to be 2. And that is my second equation there. So at this point, we've got simultaneous equations. So minus V1 add V2 is 2. And then 2V1 add 6V2 is equal to minus 28. And these are my two equations. So now I need to solve them simultaneously. Solve them however you like, but we need to find the speeds v1, v2. So what I can do, well actually I could double the first equation. So that'll get me minus 2v1 and 2v2 to be 4. Then if I bring down the second equation, rewrite it here, you can see if I now add these two equations, it cancels out the v1s, right? Because minus 2v1 add 2v1 goes to 0. So all we're left with is 8 lots of v2 to be 4, take away 28. And that goes to minus 24. Okay. Okay, then I can just divide by 8. The v2 is just going to be minus 3. And there we are. That is my velocity v2 there. Okay. Now that's negative, that's fine. If I go back to now my original diagram, so v2 is minus 3. So if I say minus 3 here, well, that is again saying that I need to flip the direction. It's not going forward, it's actually going backwards. So we flip it, that tells me it's going positive 3 backwards. So indeed it's going backwards. That's the true direction. Okay. And so there we are. Now we can also then find v1. Okay, let's continue solving. So I'm going to substitute v2 back into one of the equations. Let's say I substitute it into the first one, right? So minus v1, add v2 to be 2. So that means we get minus v1, add minus 3 for v2 equal to 2. Therefore minus v1, if we add 3, we get 5. Okay. Therefore v1 is simply minus 5 then, right? And there we are. And again, this is negative, right? So if we say it's minus 5 then for v1, well, again, that's saying we have to reverse, we have to change the direction. So we need to flip it, and there we are, it's positive now. So that is telling me my answer is positive here. It tells me it is indeed actually moving backwards, okay? And so there we are. So these are my velocities, okay? So A moves 5 meters per second backwards and B moves 3 meters per second backwards, okay? That's my velocity there. Okay, then it's saying to also find the impulse for each sphere. Now, the impulse, remember, so what's happening is A will push into B like this. So that means B will then receive an impulse here, okay? And so remember, impulse is sort of like the pushing effect. So if one particle pushes into another, that's where the impulse is, okay? So A pushes into B like this, so we get the impulse here. Likewise, B will push into A like that. So A will have an impulse oppositely here, okay? So these are my impulses, okay? And so actually, if I want to find the impulse now, let me just consider each, well, one of the, I only need one, right? Because the impulses are equal. So to find the impulse, let's just consider one of them. Let's consider just A, okay? So I'm going to copy the diagram from A here. There we are. Have I copied it right? I hope so. Yes, okay, cool. So that's just a diagram from A, just copied it. Now, to find the impulse, again, impulse is mv take away mu. So in this case, my impulse, now, this is going in the negative direction. Remember, it's going backwards, forwards is positive. So like with our speed, we need to negate in the negative direction. So it has to be minus I to account for the negative direction, okay? And so minus I is going to be the mass, which is 2 lots of the final speed, which again would be minus 5, because that's going in the negative direction. And then take away 2 lots of 4, okay? And there we are. Hopefully happy with all the negatives. Okay, the negatives are here to account for the negative direction. Okay, so minus I is going to be then minus 10 minus 8. So therefore minus I is minus 18. Therefore I is just positive 18 as expected. And there we are. That is my impulse there. Okay. So there we are. Now, we could also consider B if we want to. So that's the impulse, right? If we should get the same answer by also then, if we just consider B now, right? Because the impulses are the same, so we should get the same answer no matter what particle we consider. So I'm now going to copy out B. Again, have I copied that right? I just need to flip this. There we are. Okay, so this is my diagram for B. Again, impulse I is going to be mv take away mu. Well, in this case, it's positive I because it's going forward in the positive direction. That's going to be mass of 6 take away minus 3 because that's going backwards, negative, minus 6 lots of, and that'll be again minus 6 here because that's also going in the negative direction. So we simplify this, we get I to be minus 18, add 36, and so therefore we indeed get 18, okay? And there we are. So no matter what particle you choose to consider, you should get the same answer because the impulses are equal on both the particles. And there we are. Okay, then I've got this question here. So now there's going to be a bit of algebra involved because we've got m's here, but the process is going to be exactly the same. So again, we've got two particles P and Q. In this case, the mass of P is 2m and the mass of Q is 3m. And so there we are. And I'm told that they're moving in opposite directions towards each other. So that means, again, P is going to go to Q and Q is going to go to P like this, okay? And both their speeds are U, okay? So U and U here. Hopefully happy with this. Then I'm told that Q is brought to rest after the collision. So that means Q is going to end up with 0 speed. It's not going to move anywhere, okay? What about P? We're not told where P is going to go. So again, let's just assume it's just going forward, right? So if you don't know the direction, probably best to just assume it goes forward, right? And so there we are. And so we're gonna so firstly, if I call this V1, then if I call this V1, so firstly, if I apply momentum, so my usual equations, right? My usual equations. So momentum first, that's going to be 2m lots of u from P and 3m lots of minus u for Q, because that u is going backwards in the negative direction. Make it negative. That's going to be 2m lots of V1 and 3m lots of 0. Okay, so this will simplify to 2mu minus 3mu equal to 2mv1. Now this looks a bit horrible, right? There's m's and u's. Please do not be put off by the algebra here. Now a very, very, very common step we can do here is we can cancel the m's. So if we divide through by the m, there's m's in every term, so we can literally just get rid of them all like this. So we're just left with 2u take away 3u is 2v1. And actually we can then add up the u's. So 2v1 is going to be minus u. And then if divide by 2, we get v1 to be minus a half u. Okay, and there we are. And so we have a negative answer here. So v1, if I look here then, v1 is minus a half u. So the negative, it tells me I need to actually flip the direction. Okay, and then it'd be positive a half u. Okay, so that tells me indeed it's actually moving backwards there. Okay, hopefully happy with that. And so that's the speed of P. Now remember, speed is always the positive answer. So actually, so this is a velocity, right? The velocity is negative. So therefore the speed is going to be the positive of just a half u. Okay, hopefully happy with that. Okay. Okay, then it wants to find the restitution. So again, that's going to use E, which is V2 take away V1 over U1 take away U2. Okay, well in this case, V2 is actually 0. And then we're going to be taking away V1. Now, the direction is negative, so we need to negate our answer. Okay, so it's going to be 0 take away minus a half u. Okay, and so there we are. Just a very important thing to clarify here. For my restitution here, I negated the speed. The speed here is positive because it's telling me I'm moving backwards, but the direction is negative. So in my equations, I need to incorporate the negative direction. So I need to negate my answer. My answer's positive, okay, but I need to negate the answer to account for the negative direction. Anyway, hopefully happy with the key distinction there between the my answer being positive and the direction being negative. Okay. Anyway, so there we are. Then U1 take away U2. Well, U1 is U and U2 is also U. Okay, but this U here is negative. Because it's going in the negative direction, so it's going to be u take away minus u. Okay, so that's going to be positive a half u over u plus u, and so if we keep simplifying, we get a half u over 2u, and actually then we can cancel the u's out, so it's going to be a half over 2. Now you could work this out on your calculator, but if you're struggling to work that out, split it up to a half and then literally divide it by 2 like this, and then we can do a half times 1 over 2, and that'd be a quarter. Okay, so you should get the answer of a quarter for E. Okay, and there we are. So hopefully you are happy with that. Okay, and then I've got this question here. So it looks a bit uglier, this question, but let's just stick with it. So here we have two particles, A and B, of mass m and 3m. Particle A is moving with speed 2u and then collides with B. B is moving in the same direction with speed u. After the collision, B moves with speed ku. Okay, so again, part A, pretty standard. We need to work out the speed of one of the particles after the collision. So if I draw my diagram first, so again I've got these two particles A and B. The mass of A is m and the mass of B is 3m. And then A is going to collide with B, so A is going to go in towards B like this, and the speed of A is 2u. And for B, we're told that B is moving in the same direction as A. So if A is moving forward, it's going to also move forwards, okay? And it just has speed u, okay? Now, if we just take ourselves out of this for a sec, make sure make sure it makes sense that these are actually going to collide because A is moving faster than B. 2u is bigger than u, so A will catch up and collide with B. Okay, it's always good to sort of build that intuition, right? It allows for deeper understanding. But there we are. So hopefully you can understand what's going on there. Now, I'm told after the collision, B moves with speed ku. Now we're not told any direction, so again you could assume that they're both just going forwards, right? That's fine. Actually, B has to go forwards in this case, right? B has to continue going forwards because if they're both moving forwards, again, just think more, I guess, more in common sense wise or physics wise. If you've got these two balls going forward, A is going to push into B, and that'll push B even further forwards, okay? So B has to move forwards, and then let's say A is also moving forwards, okay? Hopefully happy with this, okay? Now, I'm not told what the coefficient restitution is. It's just E. Okay, I'm just to leave it as E. And actually, we actually know what V2 is because we're told in the question, after the collision, B moves with speed KU. So it's actually KU here, okay? So we just need to find V1 then, really. So again, we're going to just apply momentum first. And so that's going to be M lots of 2U as 3M lots of U. It's going to be M lots of, it's going to equal M lots of V1 add 3M lots of KU. Again, there's algebra in here, but it's the exact same steps, okay? Don't be put off. So we have 2MU add 3MU, which is MV1 add 3MKU, okay? Now, what we can do right away is divide and get rid of the M's. There's M in every term, so we just get 2U add 3U to be V1 add 3KU. Hopefully happy with this. And actually I can simplify to get 5U then is V1 add 3KU. Then if I subtract 3KU, I just get V1 to be 5U take away 3KU. Actually I can tidy this up because I can factor U out. So it'd be U lots of 5 minus 3K. And that is my expression for the speed of A. So hopefully happy with that, right? Hopefully happy with the what's going on there. So we just use momentum, but there's a bit of algebra, right? But hopefully happy with that. Then part B says, by using Newton's law of restitution, show that actually K has to be between 5/4 and 3/2. Okay, how on earth do we get to that? It looks like a random inequality, right? So it tells us to use Newton's law of restitution. So we're going to be using restitution. Now, it says Newton's law. You might hear restitution be referred to as what we call Newton's experimental law. So it's another one of Newton's laws, right? So obviously the first, second, third law, which you may be familiar with from normal maths, mechanics. This is just another one of his laws, okay? So you might, especially mark schemes, or in mark schemes, you might hear restitution be referred to as NEL, which is short for Newton's experimental law, okay? So they're the same thing, okay? So we need to then consider restitution, right, for the next part. And again, restitution, which is E. And again, E is V2 take away V1 over U1 take away U2. So in this case, V2 is KU and V1 is just V1, right? So it's going to be KU take away V1. And then U1 take away U2 is going to be 2U take away U. Okay? So that'll simplify to KU take away V1 over U. Hopefully happy with that. So therefore E is KU take away V1 over U. Okay? Now, we don't know what E is. So what we're going to have to do here is we're going to have to times across and just say E lots of U is KU minus V1. Okay? And therefore V1, if it's going to be KU take away EU if I rearrange. And so there we are. So even more letters now. But again, weird algebra, but hope the steps are the same. So I can also factor a U out, and that'd be K minus E. And there we are. That is my expression for V1 there. Now, this looks ugly, right? This looks a bit weird. But actually notice, I've now got two expressions for V1. I've got this expression here, but also from part A, from momentum, this as well. So obviously they have to be the same, right? They're both V1. So therefore we can say that U lots of, 5 minus 3K has to equal the U of K minus E, right? And so we can get some sort of equation from this, right? So actually, firstly, I can divide by U, cancel the U's. So 5 minus 3K is K minus E. Now the question is, it wants us to get this inequality for K. So it's in terms of k. So let's almost sort of solve for k here. So I have 5 minus 3k is k minus e. If I then add 3k to both sides, I get 5 equals 3k add k is 4k take away e. Therefore 4k is e plus 5. Okay, and therefore k is going to be a quarter of e plus 5. And that is my expression for k. Okay. Now, how on earth am I going to get an inequality from this? If we look at the answer they want, there's no e involved. It's just between 5 over 4 and 3 over 2, right? K is between 5 over 4 and 3 over 2. There's no e. That gives us a hint, okay? Our answer does involve an e. So to get an inequality, remember we looked at a similar problem at the start of this little section. Remember we looked at how we can use e, and remember e is between 0 and 1. We can use this inequality for e to get an inequality for something else, right? So if we look at the expression, it's a quarter lots of e plus 5. So we can start from e being between 0 and 1 and work our way up. So what we can then do is we can add 5 to both sides. So e plus 5 is between 5 and 6. And then we can multiply by a quarter, okay, to both sides of the inequality. So it'd be 5 over 4 between a quarter of e plus 5 between 6 over 4. Hopefully happy with all this, right? And actually, this is k, right? This expression is k. So then we can finally say that k is between 5 over 4 and 6 over 4. And actually 6 over 4 cancels down to 3 over 2. And that is the inequality they wanted in the question. So yes, you must make sure that you remember that e is between 0 and 1, because it will help to gather an inequality based on that, okay, like with this question here. Okay, so you must have that in the back of your mind. And then I've got this example here. So here we're told two balls P and Q of masses 3m and 4m. They're moving in opposite directions towards each other. Before they collide, P has speed 3u and Q has speed 2u. Coefficient restitution is just e. Blah blah blah. So we need to find the speed of Q. So we basically need to, again, as usual, work out the speeds first. So we're going to first draw our diagram, okay? P and Q. Now, obviously, again, the expression looks horrible, but again, it's just algebra. We're going to be doing the exact same steps, so please don't panic. Now, for P, the mass is 3m and Q is 4m. And then we're told they're moving in opposite directions towards each other. So P is going to go to Q. Actually, I should... here we are. So P is going to go to Q like this, and Q is going to go to P like that. Okay. And I'm told P has speed 3u here, and Q has speed 2u. And so hopefully happy with this, right? Now, I'm not told what happens after the collision. I'm not told what direction they're moving in. So again, a very safe thing to do really is to assume that they're just both going forwards. Okay, that's sort of the default assumption if you're not given a direction. But there we are. So this is V2 and this is V1 here. Okay, again, if we have got the wrong direction, that's fine. My answer will be negative, so I just need to reverse it. Doesn't matter, but here we are. Okay, so hopefully happy with that. So again, we're going to apply our usual technique. So momentum is going to be 3m lots of 3u, add 4m lots of negative 2u, because that's going in the negative direction backwards. That's going to be 3m lots of V1, add 4m lots of V2. Then if we expand, we get 9mu, take away 8mu is going to be 3mV1, add 4mV2. Then we can get rid of the m's. And so we get 9u take away 8u is 3v1 add 4v2. And actually this simplifies to 3v1 add 4v2 to be u. And that is my first equation there. Okay, then if I use restitution, so again, E is V2 take away V1 over U1 take away U2. So obviously we have V2 and V1 here, so just V2 take away V1. And then U1 take away U2, well U1 is 3U and U2 is 2U. So that, and this is negative as well, right? And the neg is going in the negative direction, so we need to negate it. So it's 3U take away minus 2U. Okay. Hopefully happy with that. So this simplifies to V2 take away V1 over 3U add 2U. And so that's E, right? So E is equal to V2 take away V1 over 5U. Now, we're not told what E is, it's just E. So if we then if we multiply, we get 5EU is V2 take away V1. And there we are, okay. Now, again, this looks ugly. There's E's and U's and M's and all that. Again, please don't be bogged down by the algebra. This is going to be the standard procedure, right? Pretty much every question in this chapter to do with collisions like this, it's the same sort of procedure here, right? So hopefully you can grasp what I'm doing here. So I'm just applying the standard method we've been looking at so far. So again, now I'm going to solve them simultaneously. So minus V1 and V2 is indeed 5EU, but also 3V1 add 4V2 is U. Okay. So I'm going to solve them simultaneously. Again, it looks horrible because there's loads of letters. But actually, spot that we can just triple the first equation. So I have minus 3v1 add 3v2 to be 15EU. And then if I rewrite the second equation, so 3v1 add 4v2 equal to u. And actually then spot we can get rid of the v1s if we add the equations. So minus v1 and 3v1 goes away. So we're just left with 7v2 is 15EU add u. So hopefully happy with that. And then I can just divide by 7, right? So it'd be a seventh of 15e plus 15EU plus u. And then we can actually pull out a u as well. So it's a seventh u lots of 15e plus 1. And there we are. And so there we are. So again, quite a weird algebra, a lot of letters EUs. But again, hopefully happy with that. Of course, I'm also going to want to find V1. So sub V2 back into one of the equations. Let's say I substitute it into the first one here. So minus V1 and V2 is 5EU. So therefore, we have minus V1 and V2, which is now a seventh U of 15E plus 1 to be 5EU. Okay, then hopefully you can see that V1 then is going to be a seventh U 15E plus 1 take away 5EU when I rearrange. Now, obviously, I'm going to want to tidy this up. So let's firstly expand. So it's going to be a seventh U times 15E is going to be 15 over sevenths, lots of EU. Add a seventh U, take away 5 EU. And then spot, again, I can collect the EUs. So 15 over 7 lots of EU, take away 5 lots of EU is going to be minus 20 over 7 lots of EU. And then add the 7th U. And actually then we can pull out a factor of a 7th U. So we're going to be left with 1 take away 20E. And that is my expression for V1 there. Okay. And so, yeah, we want to factorize it as much as we can and simplify it. But hopefully happy with that. Again, very, quite weird algebra. But when you practice enough of these, it's very, very common exam sort of question this is, as you'll see in a second. But hopefully once you grasp this and you practice it enough, it should be pretty easy and pretty routine, but it looks scary for the first time, but hopefully you're happy with the steps here. Okay, so the question says it wanted the speed of q, which is going to be v2, to be u over 7 of 15e plus 1. Well, actually, look at my answer. That is what they've got. This is the exact same expression, right? And so we got it right. Okay, so hopefully happy with that. Okay, so there we are. Then it says in part B, given that the direction of motion of P is unchanged, find the range of possible values of E. So the direction of motion is unchanged. That means, as we were told, P is moving forwards. So if it's going to be unchanged, it's still going to have to move forwards after the collision, which means that V1 has to be a positive answer. V1 has to be a positive number, because let's say if it was, let's say -2, that tells me I'd have to reverse the direction. But the question say no, don't reverse it, keep it in the same direction. So we have to make sure the answer is positive, which tells me I am indeed moving forward. Hopefully happy with that. So V2, again, I don't know what V2 is, but it has to be positive. All right, because that tells me do not change the direction, do not flip it. Hopefully happy with that. So what we need to consider is that V2 must be positive. Okay. Oh, V2 must be positive. So it continues moving forward. Oh no, sorry, V1, sorry, it's V1, not V2. I'm getting it mixed up. Sorry. So if V1 must be positive, that just means V1 has to be greater than 0, right? And so if we sub in our expression for V1, that's going to be a 7th u of 1 minus 20e has to be greater than 0. Hopefully happy with that. I'm just substituting that expression in, which we found here, right? So we just proceed to solve the inequality. Now it's looking for the values of E, so we kind of need to solve for E here. Now, what we can do is divide by 7th u, right? Almost like an equation. So we get 1 minus 20e is greater than 0. Now, you're right to question, are we allowed to divide by that? Because would that affect the inequality? Because remember, inequalities, if you divide by negative, it would flip it. No, because u is a positive number. Okay, u is a positive number. Why? Because it's a speed. Okay, remember, if you look at the question refers to u as a speed. So speed free u. U has to be a speed quantity. And remember, speed is always positive. Okay, so if u is a speed and speed is positive, therefore u is positive. Okay, so that's the justification there. And you'll see quite a few exam questions you have to do this sort of technique. You can always just divide by the u pretty much, but hopefully happy with that. So we can just cancel out the 7th u. So we're just left with this, and this is quite nice to solve now, right? So if I add 20e like this, therefore 1 over 20 is greater than e. Actually, then we can flip that to then say that e is just less than 1 over 20. Okay, and there we are. That is my answer. That's the range of values of e. However, we can be a bit more, we can be better than this, can't we? We can say we can tighten this inequality, because not only does it have to be less than 1 over 20. Remember, and you should have this at the back of your mind, e is between 0 and 1 always. So if e is less than 1 over 20, that means my final E is between 0 and 1 over 20. Okay, so this is actually my final proper answer here. These are the full possible range of values for E. Please do not forget that inequality. Okay, you may lose a mark if you don't include the full inequality. Okay, hopefully you're happy with that. Okay, now part C is now again asking for impulse. So we're told the impulse is 10 mu over 9. Now we can find the value of E. Now again, impulses, again the impulse. So first, if P is going to push into Q like this, Q will have an impulse here. Likewise, Q will push into P, so P will have an impulse here. Okay, hope you're happy with that. Again, pretty standard. The impulses will act like this. So let's just consider what should be V1 here. Sorry. Let's just consider one of the particles, right? You can take your pick, really. Let's consider. I don't know. I chose P. I chose the first one last time, so let's consider this one now. Okay. So if I just consider Q, again impulse. So impulse is I is mv take away mu. Now we know what the impulse is actually. The impulse we're told is 80 mu over 9. So we can sub that in, right? So 80 mu over 9. Or 80 over 9 lots of mu. And so the impulse of 80 over 9 mu is going to be mv take away mu, where the mass is 4m. Okay, please don't get the m's confused, right? So it's 4m for the mass. Okay, that's what I'm referring to. So 4m times v, so v2 here, take away 4m of the initial speed. Now it's 2. Now initially it's 2u, but it's in the negative direction, so it's minus 2u here. Okay, then if we just simplify this, we'll get 80 over 9 mu. It's going to be 4mv2. Add 8 mu. Actually, then we can get rid of the m's, and so we get 80 over 9u is going to be 4v2 add 8u, and actually we can rearrange for v here, v2 here. Okay, so that means 80 over 9u take away 8u is 4v2. Actually, then, if we collect the u's now, we have 80 over 9 take away 8. That's 8 over 9u. Okay, and there we are. Therefore, v2. If we divide by 4, we get 2 over 9 lots of u, and there we are. That is expression of v2 here. Hopefully happy with that. So I'm just applying the impulse formula here, which you should be familiar with from chapter 1. But hopefully happy with that. Again, there's a bit of algebra here, but hopefully happy with that. But also, well, we know what V2 is. We also know from part A that V2 is this expression here. So V2 is going to be a 7th u of, was it 15e plus 1, was it? Yes, 15e plus 1. So that's the expression we worked out before. This is V1. This is V2. That's going to equal the other expression for V2, which we worked out to be 2 over 9u. So hopefully you're happy with this, okay? Now, what we can now solve for E, right? So actually, I can get rid of the u's, firstly, straight away, cancel the u out. So we just get a 7th of 15e plus 1 to be 2 over 9. Then if we divide by a 7th to get rid of the 7th, so that means 15e plus 1 is going to be 2 over 9 divided by 1 over 7. And that will get me 14 over 9. Okay. And therefore 15e, if I subtract 1, I get 5 over 9. Therefore, divide by 15, I get E to be 1 over 27. Okay, and that is my value for E here. Okay, and there we are. So hopefully you're happy with that, and that all makes sense. Again, make sure you're comfortable with the algebra. Make sure you go step by step. You're happy with everything I've done there. Okay, but there we are. And then we got this exam question here. So here we're told a particle of mass 2m is moving with speed 2u on a smooth horizontal plane. Particle P collides with particle Q of mass 3m, which is at rest. The coefficient restitution is E. Immediately after the collision, the speed of Q is v. And for part A, we need to get this expression for the speed of Q here. Okay. Now, let's not be too bogged down, because we're just going to be doing the exact same method we've been doing all this time. So, firstly, we draw our two particles. So, we have P and Q. And so, the masses, well, P has mass 2m. And Q has mass 3m. Okay. Then we label my speeds. So I'm told that for P, it has speed 2u. So it's going to go towards Q with speed 2u. And actually for Q, it's at rest. So that means initially it has 0 speed. Okay. Hopefully happy with this. And so afterwards, well, again, if you can just visualize this, okay, if P is going to push into Q. Okay, and Q is going to roll forward, so it's going to move forwards. Okay, I'm going to call that V2, and then let's say, well, actually, the question kind of hints where P will go, because we're told that the direction of motion of P is reversed. So that means if that's saying that the direction of P afterwards is going opposite to where it was before. So before it was going forwards, so the direction now afterwards has to be opposite. Okay, so it's going backwards instead. Hopefully happy with that. I'm going to call that V1. Okay, so hopefully happy with all of that. Then we just apply the normal procedure. Okay, so firstly momentum. Okay, so for P it's 2m, lots of 2u. And then for Q it's 3m, lots of 0. Right? And so then afterwards it's going to equal 2m, lots of minus v1, because again we're treating forwards as a positive direction. So it's minus v1, and then 3m, lots of v2. Okay? And so if we expand all of this, we get 4mu is going to equal minus 2mv1 add 3mv2. And what we can do here is we can divide by the m's to cancel all the m's, which makes my life a lot easier. So I have 4u is going to be minus 2v1 add 3v2. Now that's my equation here. Okay. Then we're going to then apply restitution. Now the issue is, we don't know what E is exactly. It's just E, but that's not actually going to be a problem because we're still going to apply the same procedure. So E, again, my standard formula, E is V2 take away V1 over U1 take away U2. Okay, well, so we have V2 and V1 here. But the V1 is in the negative direction, so it's going to be V2 take away minus V1, okay, to account for the negative direction. Then U1 take away U2, well, it's going to be 2U take away 0, so it's just 2U, right? So that's simplified to V2 and V1 over 2U. Now, remember, this is equal to E. So actually we can cross multiply to deduce that 2EU is V1 and V2. And that's my second equation there. Okay. And so then if I bring these equations together, I'm going to rewrite them. Okay, these are my two equations. Again, these are simultaneous equations. They're not the nicest looking ones, but even though there's just algebra here, we do the exact same steps. Okay, do not be scared by the algebra. So the idea is I want to eliminate either V1 or V2. So what I can do is double the first equation. So I'm going to get 2V1 and 2V2 is 4EU. And then if I rewrite the second equation down here, hopefully you can spot how I can get rid of V1. I can add the equations together, right? Because then it will cancel the V1s. So I'm left with 2V2 add 3V2 is 5V2 is 4EU add 4U. And so if I then divide by 5, I just get V2 to be a fifth lots of this. Okay. Hopefully you can spot I can simplify this a bit nicer. I can factor a common factor of 4 lots of U. So a 4/5 of U. And then if I factor that out, it's going to be E plus 1. Hopefully happy with this factorisation here. Okay. So I pulled out a factor of 4U. And so there we are. And that is my final simplified expression for V2. And actually, look what they've said. It actually matches the expression they wanted. Indeed, the speed of Q, V2, is 4U over 5 of 1 plus E. That is the exact same expression we've got here. Okay, so we know we've done it right. That's great. Now, 99% of the time, you're going to also need V1, the corresponding speed, right? The other speed for P. So we're going to need to continue solving this for V1. So what we're going to do is we're going to sub V2 back into one of the equations. So let's say I substitute it into the first one up here, right? So V1 and V2 is 2EU. And so then I get that V1 add V2, which is 4 over 5U. Lots of E plus 1 is going to be 2EU. Okay. Then I can just get V1 if I subtract the 4/5 U of E plus 1. I get this. Okay. And there we are. And then I can actually make this a lot nicer if I first expand. So I get 2EU minus 4/5 EU minus 4/5 U. I expand the brackets. Then actually notice I can collect like terms for EU. So 2 lots of EU take away 4/5 lots of EU. I get 6/5 lots of EU. Take away 4/5 U. And that's V1. Then hopefully you can spot I can take out a common factor of 1 over 5 lots of U. Okay, 1/5 lots of U. And so that would be 6E minus 4. Okay, I could actually factor out a 2 as well if I wanted to, but I'm going to leave that there. And that is my final expression for V1. So hopefully happy with that. So this is very standard exam question. This is so hopefully happy with all of this. Okay, very common procedure that is. Again, there's a lot of algebra here. We've got E's and U's, but the process is exactly the same. And hopefully happy with the algebra here. So I've got my final speeds V1 and V2 now, right? Now, what's the next question saying? It's saying that we need to show that V, so this is again referring to the speed of Q here, that V or V2 is between 4U over 5 and 8U over 5. Hopefully you recognise that's going to be pretty similar to one of the problems we looked at the intro to this part of the video. So we looked at a problem like this. So we need to show that V2 is between, was it 4U over 5, was that it? 4U over 5 and 8U over 5, okay? That's what we need to get to. How are we going to do that? Well, if I recall that V2, again from part A, is 4/5 U, lots of E plus 1. How are we going to find this inequality from this? Well, actually notice there's an E here but there's no E there. That's a big clue. How can we get an inequality with E? Hopefully you're screaming that it needs to be between 0 and 1. That's a stat. That's the inequality you must remember for E. So what we can do then is go from E, and then we can sort of, and then work our way up to this whole expression here. Okay. So firstly, if I'm starting from E, let's add 1. Okay. So therefore 1 is between E plus 1 and 2. Okay, so now we've got the bracket E plus 1, then we need to multiply it by 4/5 U. So we need to multiply the whole inequality by 4/5 U. So 1 times 4/5 U is just 4/5 U. Then 4/5 U, lots of E plus 1. And then 2 times 4/5 U is going to be 8/5 U. Okay. And actually then, this is V2, right? This is V2. So actually, therefore, we get the answer that it's between 4/5 U, V2, and 8/5 U. And that is the inequality they want there. Okay? So hopefully happy with that, okay? Hopefully happy with that. Then the final part of the question, it's asking that given the direction of motion of P is reversed, find the speed of P after the collision. Okay, well actually we did just that, right? We've already done that, right? So initially it's going forward, then it's been reversed backwards. Well actually no, we've done our answer then. That the speed of P is V1. So we've done part C already. Okay, so there we are. But see what I mean though? See when I said that you're going to need to find both speeds. Well, there we are. We needed to find it in part C. So we did all the work anyway. So we should get all the marks there. Okay. And so there we are. So hopefully you're happy with that. So we've got this exam question here. So we're told two particles P and Q of masses M and EM respectively. Particles are moving on the smooth horizontal plane in the same direction along the same straight line. When they collide directly, the coefficient of restitution is E. Immediately before the collision, the speed of P is U and the speed of Q is EU. Show that the speed of Q is U. Okay, so again, we just need to consider my my speed. So if I draw a diagram, I have P and Q, and P has mass M and Q has mass EM, which is quite interesting. It involves E. So there we are. Then the speed, we're told they're moving in the same direction. Okay, so P is going to move forwards, as is Q. Okay, in the same direction. And I'm told that the speed of P is U here and the speed of Q is EU. Okay, hopefully happy with me here. So the speeds are going to be V2 and V1. Let's say they're both moving forward. Okay, and so then momentum firstly. So firstly, it's going to be M lots of U, and then EM lots of EU. It's going to equal M lots of V1, and then EM lots of V2. Okay, so if we simplify this, we're going to get MU and E squared MU equals MV1 and EMV2. Again, there's a lot of weird algebra, but it's the same method. Okay, the same idea. Okay, we can divide by M, cancel all the M's out, so we're going to get U and E squared U is going to equal V1 and V1 add EV2. Okay, and that's my equation here. Then restitution, that's going to be E. Right, again, that's going to equal V2 minus V1 over U1 minus U2. Well, that's going to be V2 take away V1. Again, we have V2 take away V1 here. Then it's going to be U take away EU. Now, they're all positive. They're all in the positive direction. So we can just take them away like this. Okay. So hopefully happy here. And so then if I cross multiply, I get E lots of U minus EU is equal to V2 take away V1. Okay. if I can expand this to get EU take away E squared U is equal to V2 take away V1. And so I get these two equations here. Again, they're not the nicest looking equations, but again, it's the same method. So we're going to solve them simultaneously. So if I rewrite them here, I have V1 add EV2 is going to equal U add E squared U. That's my first equation. And then here, minus V1 add V2 is going to equal EU take away E squared U. Okay, now I want to solve for these V's here. So I can actually just add them, right? Because the V1s will cancel. So then I'm going to get EV2 add V2 is going to equal U plus E squared U add EU take away E squared U. This is the equation I end up with if I add these two. Now, I can actually factorise a V2 here. So V2 of E plus 1 is going to equal, now I have U and then plus EU. Now the E squared U's will cancel because I have EU squared minus EU squared. So these will actually cancel quite nicely, okay? And actually then spot I can factorise, actually no, let me just divide by E plus 1, okay? So V2 is going to be U plus EU over E plus 1. But notice I can factorise a U out. So that's going to be U lots of E plus 1 over E plus 1. But what do you know? The E plus 1's cancel. So V2 is just U. And I believe that's what they wanted me to show. That the speed of Q is U. So there we are. Okay. Then it says, show that the direction of P is unchanged. Okay, so that means again if P is originally moving forwards, it's going to continue to move forward. Now we already assumed it's moving forwards, so actually V1 has to be positive. Okay, it must be positive, okay, for it to continue moving forward. Okay, so we need to show that V1 is positive. Okay, and therefore that means it doesn't change direction. Okay, so we have V2, so we need to find V1. So we can substitute it into either equation here. Let's say I substitute it into this one. Actually, no, I think it doesn't really matter, does it? Okay, so V1 here. So I'm gonna so the first equation. So V1 add EV2 is U add E squared U. Okay, so I've just copied one of the equations we had, and now I'm going to sub V2 in. So therefore V1 add E lots of U for V2 is going to be U plus E squared U. Therefore V1 add EU is going to equal U plus E squared U. So then I can do V1 is going to be minus EU add U plus E squared U. Okay, well, I can factor a U out. So V1 is going to be U lots of minus E plus 1 plus E squared. Now, that's very interesting. We get a quadratic. If I rearrange this a little bit, this is going to be U lots of E squared minus E plus 1. Okay, now remember we need to show that V is positive. V1 then has to be greater than 0. Okay, so in other words, we need to show that U lots of E squared minus E plus 1 is greater than 0. Okay, now U has to be greater than 0 because U is the speed. Okay, remember in the question it refers to U being a speed. So the speed of P is U. U is a speed. U is a quantity for speed, and speed is always positive, so that means U is positive because it's a speed. Okay, so U has to be positive by positive. So we need to show that ultimately that e squared minus e plus 1 is also positive. Okay, how are we going to do that? Well, you can do this many ways, but I think the safest way to show that this quadratic is greater than 0 is to do completing the square. So if we complete the squareness, this is going to be e minus a half all squared, then take away a quarter plus 1. Then if we simplify this, then minus a quarter plus 1 is going to be plus 3/4. And that has to be greater than 0 because this whole thing is a square number. Square numbers has to be positive, right? But we're also adding a positive. So we're adding a positive to a positive. We're adding a square number to this positive 3/4. So the whole expression has to be positive. Okay? So therefore, V1 has to be positive. So P does not change direction. And there we are. And again, make sure you're happy with that. Hopefully that makes sense. Okay, because remember the idea is we wanted to show that V1 is positive and V1 is equal to this U, lots of e squared minus e plus 1. Now we're effectively multiplying two numbers together. We're multiplying U with this quadratic. So if U is positive, then we need to multiply by a positive quadratic. So we've shown the quadratic's positive by completing the square, and it has to be positive. Okay, right. Okay. Then in part C, it says that the magnitude of the impulse on Q is 2/9 mu. So again, if we have impulses, so Q is going to have an impulse here, and P an impulse here. And it says find the possible values of E. Okay, let's consider, I don't know, well, it's mentioning Q, so let's consider Q, okay? So if I redraw Q out here, okay, so all I've done there will just copy out the diagram for Q, and also V2 was U, okay, so I can add that on. Okay, so I'm told the magnitude of the impulse is 2/9 mu, okay, so if I now use impulse to be mv minus mu, that's my formula, right? So I is going to equal, well, the mass is em, and then the final speed is u, take away em of the initial speed eu, okay? And I'm told the impulse again, the impulse was 2/9 mu, so I can equate this to 2/9 mu. That's going to equal emu minus e squared mu. Okay, now I can actually cancel the mu's out, right? I've got an mu here, an mu here, and an mu here. So I get 2/9 equals e minus e squared. And what do you know? I get another quadratic now. I get minus e squared plus e minus 2/9 equals 0. Okay. So I can solve this quadratic. You can solve it however you want. So if I use just a quadratic formula, e is going to be -1 plus or minus the root of 1 squared minus 4 lots of -1 lots of minus 2/9 over 2 lots of -1. So if I solve this quadratic equation for e now, I get e to be 2/3 or e to be 1/3. Okay, now both of these are plausible values, right? Both of these values are between 0 and 1. Okay, By the way, I should say I do not include 0 and 1 here because the question specifically says it specifically says is between 0 and 1. It can't be equal to. Okay, but honestly, it doesn't really matter here. Just thought I'd just stress the fine details. Okay, but there we are. Anyway, both of these values are plausible. Okay, they're all between 0 and 1. So those are my two possible values for E. Okay, and there we are. Okay. So quite interesting question that is. But it includes quadratics and stuff like that. But again, like I said, the algebra might be weird, but the process is the same, right? So yeah, make sure you're really up to scratch with your algebra here. Okay, but hopefully that made sense.